Today's lesson is about quadratic functions. By the end of the lesson, you should understand that a quadratic relationship or a quadratic function is a polynomial of degree 2. You should know how to identify a quadratic relationship using a second order difference. You should recall that a quadratic equation is a parabola and recognize the critical features of a parabola. You should also understand how to dilate and refract a parabola and be able to determine the domain and range of a quadratic function. And finally, you should be able to recognize a parabola in general form and identify the critical features of the parabola. Now, in real life, where do we see the use of a parabola? Here, this picture is a Roman aqueduct. You can see that there are parabolas in there. This is a satellite dish. The back of the satellite dish is the shape of a parabola, and it concentrates the microwave or any sort of signal coming in to the tip of the satellite dish. A bridge, it's a cable bridge with a cable in the shape of a parabola, and downlight. Basically, this is the same as the satellite dish. So the back of it concentrates the light. And finally, the fountain. The fountain is in the shape of parabola. Also, the other use of a parabola is actually to analyze projectile motion. If you are interested in sports science, you probably will be using it when you're analyzing kicking ball and so on and so forth. Now, another thing that parabola is used quite widely is in architecture. A few years ago, I visited Barcelona and I took a picture of Gaudi, the architect, the picture of the model of the church by Gaudi, the architect who designed the church. So what he did was to hang chains from the ceiling, and this picture here represents the reflection of the chain from ceiling. And then what he did was, based on the reflection, he created the model of the church. So you can see that it is widely used. The quadratic functions or quadratic relations, we can look at the general form of the quadratic or functions or relationship, which is y equals to ax squared plus bx plus c. Now we know that polynomial has a general formula of this y equals to an, x to the power of n, and so on and so forth. And for quadratic, that's a power of 2, and cubic is a power of 3. These are actually the degree of the polynomial. Please recall that from what you have learned in year 10. So, the degree of the polynomial is the highest power of the of x. So therefore, for quadratic function, since x is to the power of 2, it is a polynomial with a degree of 2. Note that in this case, a must be greater than 0 or less than 0. It cannot be equal to 0. If it is equal to 0, it becomes a linear function. Now, let's see if we could recognize a parabola or quadratic functions from a table of values. You are given a table like this. How do you tell whether it's a parabola, or it could be a cubic function, or it could be a linear function? First, let's have a look at the difference in y from when we change x. You can see that with x going up by 1 unit, y actually goes up by 2 units. So this is called the first order difference. When it is constant, in this case, you can see that for every 1 unit increase in x, y increases by 2 units. And this actually is a linear function. And the first order difference in this case, 2, is actually gradient of y equals to mx plus c. Now, let's have a look at a different situation. This table here. We looked at the first order difference. It is not actually a constant. Then, we look at the second order difference. Notice that it is a constant. So the second order difference here actually tells us that this is a quadratic function. It's y to the power of something x squared. Alright? Or let's look at it as y equals to ax squared plus bx plus c. We don't know how to determine a, b, and c yet. We'll do it a little bit later. Alright? What about this? Let's have a look at the first order difference. No, it doesn't work. But when we look at the second order difference, it is a constant plus 2. Therefore, we know that this is a quadratic function. Now, this one, I want you to pause the video for about a minute and work out whether it is a quadratic or linear. Right. Let's reveal the answer. This is actually a quadratic function. Again, pause the video for a minute or so. Check whether this is a quadratic or a linear function. Alright, time to reveal the results. It is actually a quadratic function. I want you to use your class pad. Take your class pad out and actually plot y equals to x squared. Pause the video for a couple of minutes. Do that, please. Now, if you've done it correctly, it should look something like this. Alright, you can see that y equals to x squared is actually the shape of a parabola. Let me explain what a parabola is. Now, parabola is a quadratic function. It is a curve with an axis of symmetry and also a turning point vertex. The turning point must lie on the axis of symmetry. Let's have a look at the pictures there. One, you've got what I call a U shape and what I call an N shape. Alright, U shape is actually a concave up parabola, whereas N shape is a concave down parabola. The U shape actually has a minimum turning point or the vertex, while the N shape has a maximum turning point or the maximum vertex. The axis of symmetry is where the minimum turning point or the maximum turning point occurs. Basically, if you fold the parabola up in two along the axis of symmetry, it should become one line. One part of the parabola should cover the other part perfectly. Note that the axis of symmetry is also called the line of symmetry. Now, let's plot a parabola on a Cartesian plane. I'm only using the U-shaped parabola as a guide. Here, when you plot or sketch a parabola and a Cartesian plane, you must always indicate the axis of symmetry, the y-intercept, the turning point, and eventually you should know how to indicate the x-intercepts as well. Alright, make sure that you label your x and your y-axis, and finally label the parabola. Alright, now let's go back to y equals to x squared. I have done this using a different graphic software so that you can see it a little bit clearer rather than using your my class pad. This is the shape of y equals to x squared, and it is a parabola. The red line is actually the axis of symmetry or the line of symmetry. It happens when x equals to 0 or the y-axis. Then the vertex is also the minimum turning point. Note that most books will use turning point, although I interchange between vertex and turning point. And then look at the x-intercept and y-intercept. In this case, the x and y-intercept, they are the same, and it goes to the origin. So in fact, we can call y equals to x squared as the basic parabola. Now, we are going to look at how we could dilate the basic parabola. Dilation means whether I make it narrower or wider than the basic parabola. Again, I want you to use your class pad. Take about 1 to 2 minutes to plot y equals to x squared, y equals to half x squared, and so on and so forth. Well, let's review my answer. This is what I've done. You can see the different shape. Here, this two is this line and this line. You can see that when the coefficient in front of x squared is less than 1, the parabola is actually wider. Whereas when it is greater than 1, the parabola is narrower. Alright, we'll look into this a little bit more. Just bear that in mind. Next, again use your class pad. I would like you to plot the following equations. 4 of them. Pause the video for a while and then plot it. Alright, let's review my answer. What can you observe? What does the negative in front of the x squared or in front of the negative 2x squared does to the graph? You can see that one is reflection of the other. So minus x squared is actually a reflection of x squared. So you know that the blue line is x squared, y equals x squared, and the orange line is y equals to minus x squared. So one is the reflection of the other, and same with 2x squared. 2x squared and minus 2x squared, one is the reflection of the other along the x-axis. Now, let's do a bit of conclusion, summary of our observation. This case, we are looking at y equals to ax squared when a is not 0. First, when a is 1, we know it's a basic parabola. So what can you observe from the graphs plotted on the effect of the effect of a to the parabola? First, you can see that the value of a affects the concavity of the graph and the rate of increase and decrease of the function. So it actually affects whether it's wider or narrower than y equals to x squared. It transformed the basic parabola by stretching it in the y direction by a factor of a. So, the value of a affects the steepness of the curve. For example, the y values of each point on y equals to x squared are 4 times the y value of each point of y equals to x squared. So you can see that this 4 is stretching the parabola in the y direction by 4. So for a greater than 1, the parabola will be narrower than the basic parabola. And for 0 less than a less than 1, the parabola will be wider than the basic parabola. Now, if we have a negative in front, the parabola is actually reflected about the x-axis. So y equals to minus 2x squared is a reflection of y equals to 2x squared. What about the domain and range of y equals to ax squared? Or the function of x equals to ax squared? Irrespective of the values of a, in general, we can define the domain of x is x as a member of the real number or an element of the real number. However, let's have a look at when a equals to greater than 0. Let's quickly sketch the graph of y equals to x squared. Alright, this is a graph of y equals to x squared. This should be touching the origin. This is y equals to x squared. You can see that the range, any negative number square will be positive. Therefore, the range is greater than 0. Whereas, when we look at y equals to minus x or minus 1x, right, this is yx, y equals to minus x squared, which is a reflection of y equals to x squared. You can see that the range is actually below 0. Basic reason is if you've got minus 1000 or minus 10. Minus 10 times minus 10 is actually y equals to minus 10 square. Therefore, is minus 100. So you can see that y is actually below 0. Or, let's take another example, y equals to minus 10 square equals to minus 100. Again, you know that is below 0. Therefore, you must know the range when a is less than 0 is actually y is a member of the real number or an element of the real number, and it is less than or equal to 0. Now let's try this question. So what is the range of y equals x squared given that first, a, the domain of x. X is an element of the real number and is between minus 5 and plus 5. So you know that, let's have a look at part A. When x equals to minus 5, the whole thing square, that is 25. Alright, when y is equals to 5, or actually no, x equals to 5, y is equals to 25. Therefore, we know that the maximum number is 5. Now, when x is equals to 0, y is 0 square, and that is 0. Therefore, we can say that the range of y is actually y such that y is an element of the real number and y is greater than or equals to 0 and less than or equals to 25. Alright? Now part B. X is less than 0. Again, remember what I say. If it is negative number square would be positive number. Therefore, the range of y is y such that y is an element of the real number. This time, y must be greater than or equal to 0. It cannot be any negative numbers. Now for part C, let's look at when x is equal to minus 4. Y would be minus 4 square, which is 16. And when x is equal to 0, y is 0 square, which is 0. Therefore, we know that the range of y is actually y such that y is an element of the real number and y is greater than or equal to 0, less than or equals to 16. So you must know how to find the range of y given the domain. Then, next bit, we need to look at the general form of a quadratic equation. Y equals to ax squared plus bx plus c. Again, I must say that a does not equal to 0. Now, the line of symmetry or the axis of symmetry of y equals to ax squared plus bx plus c is x equals minus p over 2a. Since the turning point always lies on the line of symmetry, the y coordinate can be determined by substituting x equals minus b over 2a into the equation. And we need to know that for a is greater than 0, the turning point is a minimum because this is a U shape. Whereas for a less than 0, the turning point is maximum. This is an N shape. Alright? And the y-intercept can be determined by substituting x equals to 0. Hence, the y-intercept is 0c. So this one here is actually the y-intercept. Now, I'll give you an example. Let's look at the quadratic function fx equals to 2x squared minus 6x plus 1. You need to determine the line of symmetry, the nature and the location of the turning point, and the coordinate of the y-intercept. Let's go back quickly. Here is the nature, which is either maximum or minimum. Now, with the line of symmetry, we can use x equals to minus b over 2a. We know that a is 2, the coefficient of x squared, b is minus 6, the coefficient of x, and c is 1. So therefore, we know that the line of symmetry or the axis of symmetry is x equals to 1.5. You actually substitute b and a into the equation. Then we substitute x equals 1.5 into the function. Now we also know that since a is greater than 0, the turning point is a minimum. So f, the function of 1.5, x equals 1.5 equals to minus 3.5. And the coordinate of the turning point is therefore 1.5, which is the x coordinate, and minus 3.5 is the y coordinate. Looking at the equation there, you know that intercept is 0, 1. Then let's sketch the graph. Now, generally when sketching the graph, you're not given a grid paper. But in this case, I'm using a grid paper to illustrate a few points. Alright, first you've got to draw the x and y axis. With a grid paper, I know the scale. 2, 4, and 6 minus 2, 4, and 6 for the x-axis, and you can label the y-axis as well. Then I will actually first plot the turning point. You know that it's minus 1.5, minus 3.5. Then you can actually draw the y-intercept. Plot the y-intercept 0, 1. You know that there are 2 points here. You also know that this is a U shape because the turning point is a minimum. The other thing you should specify is because there's a grid, you know that the parabola is actually symmetrical, and you can actually find the point, which is the same line on the same y as the turning point, and it must be the distance between this point and the axis of symmetry must be the same as the distance between this point and the axis of symmetry, and then you can draw that. Now, this is the end of the lesson. Oh, actually, let's go back. I should actually indicate that this is the axis or the line of symmetry, which is x equals to 1.5. That's quite important. Alright, this is the end of the lesson. Hopefully, you've understand that a quadratic relationship is a polynomial of degree of 2. You should know how to identify a quadratic relationship using a second order difference. You should also recall that quadratic equation is a parabola and recognize the critical features of a parabola. You should know what the critical features are. The y-intercept, the turning point, whether it's minimum or maximum, and the line of symmetry or axis of symmetry. And you should understand how to dilate and reflect a parabola and be able to determine the domain and range of a quadratic function. And finally, you should know what a parabola is in a general form. That's the end of the lesson. Thank you for listening.